Okay, so I'm gonna thank the organizers again for inviting me here. I had a lot of fun this week. I had great discussions and really a beautiful place. Okay, so for this talk, I want to talk about something that's completely different from the lectures I gave. And so indeed, I'm gonna talk about anomalous transport in 1D. So we heard about some related things this week and in previous weeks. So I'll try to give you kind of a different way to look at this. Okay? So before I start, let me thank my collaborators, Dhar, who was here but left this morning, Braden Ware, who's my postdoc at UMass, and Utkar Sagawa, who's a student with me, also at UMass. Okay? So I'm listing a few references, and actually mostly I'm going to talk about the most recent one over here. All right, so since we're all tired and it's the end of the conference, I'm probably going to rush through the introduction. Okay? We'll probably end up early. Who knows? We'll see. Okay, so 1D is special. We have Luttinger liquids, many-body localization, and something else that we heard a lot about is this week, and I think in previous weeks too, is we have integrable points. Okay? And so given the audience, I'm probably not going to spend time explaining to you why integrability is kind of interesting. One thing that I do want to mention is that, of course, they are fine-tuned, and if in a funny way, they're very hard to avoid in 1D. And that's true when you do numerics, that's true in experiments. Another good reason is that they're exactly solvable, but like even very basic transport properties, I think there was a lot of progress over the recent years. And so I'll try to tell you about some of this. All right, so the type of like simple questions that I think we now know how to answer, or at least we're getting there, and we didn't know a few years ago, are the following. So say you take an interacting Bose gas in 1D, this is a Lieb-Linegar model, this is integrable, and you can ask about quantitative description of the dynamics. After all, the model is integrable, so how can you describe something like this Newton's cradle experiment? And you heard about this last week, if you were here. And an even simpler question, right, is asking about just finite temperature spin transport, which is in some ways some very old topic, right? It's a standard condensed matter topic. And so say you take standard models in 1D, which would be like an XXZ spin chain or Fermi-Herbert model, both of which are very relevant for experiments, both in solid state or in cold atoms for Fermi-Herbert. And you ask about spin transport, okay, or charge transport in your Fermi-Herbert model. Okay? And in particular, you can ask about AC conductivity, spin structure factor. Principle, very simple questions, right? So it's all about linear response. There's nothing fancy out of equilibrium here. It's just linear response transport. And in some way, despite the fact that those models are exactly solvable and integrable, we're only getting some handle on this very recently. And part of the surprise is a lot of it is anomalous, and that's what I'm going to try to tell you about. So of course, the reason we're getting a lot of results is from like this kind of breakthrough of generalized hydrodynamics, which you heard a lot about. And so again, I'm not going to talk about it now. Okay? And so actually, you won't need to really know generalized hydrodynamics to understand this talk. Okay? So the only picture I'm kind of going to use is the fact that you can intuitively, you can think of all the dynamics as coming from a semi-classical picture of solitons that collide, they delay each other, they carry some charge. And so you had lectures on this, and really this is what made everything that I'm going to tell you about and all those results kind of possible, okay? Thinking seriously about this picture. All right, so this is it for kind of the general introduction, so let me get to the point. Okay, so the model I'm going to talk about is just this simple XXZ spin chain. That's the phase diagram you all know. That's just a ground state phase diagram. You have a Luttinger liquid here. You have this Heisenberg point. Well, delta is 1, and you're isotropic. And if delta is larger than 1, you have an antiferromagnetic L-type ground state. So that's the ground state phase diagram. Surprise is if you look at spin transport, you basically still have some dynamical phase transition. If you want, it goes to even a very high temperature that shows up in spin transport. Okay, so that's a summary of, again, things that you've seen in many talks. Okay, but I'm just kind of reminding you in terms, so spin transport is dramatically different across this phase diagram. And the interesting thing is that if you look at, say, energy transport, it's completely boring in some ways, it's purely ballistic throughout the phase diagram. So only spin transport knows about all of this. Okay. So this is the summary. So in this regime here, where you have a Luttinger liquid ground state, the spin transport is ballistic. Okay. And so meaning if you look at your conductivity, it has a delta peak. And that's actually mostly what I'm going to talk about today. So if delta is larger than 1, despite the fact that your model is integrable, you have all those conserved quantities, spin is purely diffusive. It looks like a non-integrable system, essentially. So what it means here is you have a finite DC conductivity. So you have a finite diffusion constant. And in the middle, you have this super diffusive point. And again, there were many talks on this, okay, and debate whether this is KPZ and how you can argue it's KPZ. And so in terms of conductivity, it means that it diverges as omega to the minus 1/3. So this is super diffusion, it diverges, but it's not ballistic. So before I go further, let me just emphasize the interesting thing here are like time scales and like papers and understanding of all of these things. So the Drude weight here has a very long history. And so people have been arguing for a very long time whether this is actually non-zero at finite temperature. So now the answer may appear obvious, but it was a very long debate. And of course, this is only like a very narrow sample of all the papers on this. Okay. So many people in the audience worked on this. And so it goes back basically 20 years ago. Okay. The other regimes, however, are way more recent. Of course, okay, I'm not going to be entirely exhaustive in terms of papers, I'm sorry, and I'm also partly biased. Okay. So I would say like this diffusive regime here, we really understand since last year. Okay. And so particularly Jacopo told you about this last week. And I think we at least understand how to compute this diffusion constant now and quantitatively and quantitatively why spin transport is diffusive. And this regime here is still partly mysterious, but a lot of progress has been made. And so this was observed numerically, and there's actually an earlier paper by Marcos Niederich. But those two papers are probably the main ones that attracted a lot of attention on this. And in terms of theory, I think there's like some understanding of the exponent, and I will actually give you another explanation why you have 1/3 here. And also some, so you heard from Veer why probably you have KPZ here. So you see the timescales again, all of these results, which go way beyond the Drude weight, came like basically, they almost all published this year. Yes, everything I'm going to talk about here is half-filling. Okay. There's also some interesting stuff away from half-filling. Everything becomes ballistic, but you heard from Sarang, you could still have some things that are anomalous. Everything is half-filling. Okay, and so today I'm actually mostly going to talk about this, and just to tell you that even in that regime where spin transport is ballistic, actually like the leading correction is also completely anomalous. Okay, so it's also super diffusive. And it has a different exponent, which is 1/2, so you don't only have KPZ in life, you can have other things, but it's still very much anomalous. So if you looked, what it tells you is that spin is moving ballistically, but it broadens in a way that's super diffusive. And if you look at finite frequency, it will have this tail. Right, so before I do this, I need to spend just one slide reminding you a bit about just the gapped case, so we all are all on the same page on why we can get diffusion in integrable systems. So that's just a very nice DMRG plot in XXZ, that regime where delta is larger than 1. And you can see what I was telling you, that energy is spreading ballistically. So this is time, this is space, this is preparing a localized kind of bump, if you want. And so here you can see it spreads nice and ballistically. That's the same with spin, exactly the same parameter, delta is 1/2. And you can see it's very nice and diffusive. And so in terms of theory, let me give you a one-line explanation why that's the case, right? So it seems very weird because you have an integrable system, and what you learn from all the lectures on generalized hydrodynamics is that you have quasi-particles and they move ballistically. If everything moves ballistically, you kind of wonder how you get anything that's just not ballistic, right? And so the one-line reason is that your quasi-particles are effectively neutral. So that's the only way you can get something that's not ballistic, is effectively quasi-particles are neutral, but they're neutral in some kind of interesting way. It's a dynamical screening effect. So they're only neutral in the thermodynamic limit, if you want, where effectively they have zero charge. But as they propagate, you have some fluctuation, and this gives rise to diffusion. So I won't talk about this, but this, okay, this is some kind of just hand-wavy picture that actually goes back to Damlin/Def of why you have qualitatively diffusion here. But you can transform this into actual expressions for what the diffusion constant is. Okay, so that's a closed form expression of the diffusion constant in that regime. And the limit of high temperature, eta here is related to the anisotropy in this way. So you can just plot this, that's your diffusion constant. Okay, so there's nothing anomalous here. It's still kind of surprising to get diffusion in a system that has only ballistically spreading quasi-particle, but I think by now it's, okay, we have these complementary approaches that will give you why you have this diffusion constant here. All right, but the main topic of my talk will actually be this other phase. So this other phase, which is, you can call it easy plane or gapless, again, is the regime where you have a Luttinger liquid ground state. So in some ways, it's the most conventional and the most exotic. Okay, so it's most conventional because it has ballistic transport. That's what you would expect for integrability, so it kind of makes sense. Okay? It's the most exotic because it has a very weird Drude weight. Okay? And so it goes back to Rosen in particular, and several papers are actually cut off here. Sorry about that. Okay, so the Drude weight is the coefficient that characterizes this ballistic transport, right? And so the surprises, or like what been known for some time now, that this Drude weight has a kind of fractal dependence on this anisotropy. Okay, so that's the exact formula actually. So this Drude weight, you said, has a smooth part, and it has a part that depends on, so you write delta as, say, a cosine pi of a rational. Okay? So this function depends on the denominator of this fraction here. So if q is infinity, that is if you have an irrational, this function is 1, so you have a smooth background. But whenever you have a rational, you have one of those peaks here. So the first thing, if you see this, is like, how does that ever make sense? Okay, and this was very controversial actually. So it was first established as a lower bound by Tomasz Rosen. Okay, but I think by now there's overwhelming evidence, in particular also from GHD, that this is an exact result. Okay, so perhaps not everyone agrees, but I think most people agree by now we have a completely full formula for this. So we're supposed to take this very seriously. The actual Drude weight in that model, if you take it as a function of delta, is a completely discontinuous function that has this fractal dependence. And so if you think about it, it's a very weird result, and it's something that I think has bothered many people in the community in general, or anyone that hears about this, because it sounds very unphysical. You have a Drude weight, which is a transport coefficient, okay? And if that jumps by order 1, you change your anisotropy by order epsilon. So that sounds bad. Okay? So in particular, if you want to tell either an experimentalist or someone in numerics and you think you can actually measure this, okay, so of course something has to happen, right? And so my story will essentially be to tell you how you can make sense of this, and this actually gives you this anomalous tail, the result. Okay, so again, I'm going to assume this is exact, and I think it is, right? So that's the Drude weight, and that's our answer, and I know it analytically. This is at infinite temperature, but at any temperature, it has this property. All right, so let me make another very completely obvious statement. If you look at numerics or anything in finite time, okay, obviously all your properties have to be smooth. Okay? There's no way you're going to see something fractal. So this is essentially just by locality, right? So I have local interactions, I see a finite time. I have a Lieb-Robinson cone, so I could just say I have a finite system. And of course, I'm never going to see something fractal or discontinuous like this in a finite system. So everything you see, like in ED or in DMRG or anything or in experiments, we'll never see this, right? It will always have to be smooth. I think we all agree on this, okay? So essentially, it's also saying the Drude weight is an infinite time property, so it's not something you measure directly. You're always going to see corrections to this. So my basic argument here is going to be that I'm going to consider, so lambda is this, I'm going to write the anisotropy as cosine pi lambda, okay? And I'm going to imagine, I'm going to take a series of rational approximant to some irrational value. So I'm going to assume I want to sit on some of those peaks by taking a rational approximate and approach a completely irrational value. So this, say, could be like 1 over golden ratio or golden ratio square, and this could be a ratio of Fibonacci numbers. Okay? And so for each of those, again, values, I have those peaks, but when I approach an irrational value, I lose some Judo weight, okay, from this. All right. And of course, as you take better and better rational approximates, your values of delta are closer and closer to each other, and it's going to take longer and longer time to realize that that you're not exactly sitting at those points, right? So I guess we had similar discussions actually this week about related issues, right? So, but of course, if I put this in a computer, you try to do an irrational value, it will be always almost rational, and it's you're only going to resolve this in a very long time, right? And so I wrote something a bit schematic here that if two Hamiltonians differ by some order epsilon, so this is a bit sketchy, you need locality also to have this, but okay, they will differ after time 1 over epsilon. All right, so why does that matter? So here's the basic picture that I'm going to argue for you. Okay. So those are like two values. So the red one and the red curve that you see, so this is the optical conductivity as a function of omega. Okay? And I'm going to argue it has a tail, and you'll see consistently why it has to have a tail. And something anomalous with an exponent I don't know for now. Okay? And it also has a Judo weight, right? There's always a background Judo weight. So now I'm going to approach this value by the purple one, and the purple one is the rational approximant. Okay, so imagine I take lambda that's rational. In that case, you have a slightly larger Judo weight, so this is why you have this purple arrow that's a bit bigger. Okay, so the Judo weight is a bit bigger, and you actually have a finite DC conductivity, so this is only for the regular part. Obviously, you have Judo weight, but you see the otherwise AC conductivity is approaching a finite value. So this, I'll get to that, we know from GHD by now. Okay, so this is actually finite. So what I'm arguing is that the spectral weight has to be conserved. Okay, so it has to go somewhere. So as you take better and better rational approximate, this Judo weight is going to lower and approach this. Okay, so you lose spectral weight at the origin. The spectral weight has to go somewhere. That's the argument. Okay, the spectral weight is conserved, and it has to go somewhere, and it can only go at low frequency. That's by locality, and it's like you need to go to longer and longer time, so lower and lower frequency. So as what will happen is, again, as you approach this irrational value, this Judo weight will kind of lower. This DC value is actually going to blow up, and everything has to match, so that's, the difference in Judo weight is precisely the shaded area here. And that's like conservation of spectral weight somewhere. Does that make sense? So that's the basic picture. That's actually the whole argument. Everything I'm going to tell you relies on this. I'm going to repeat it. Everything else is kind of obvious after this, okay? Yeah, so there's a global sum rule that you can show, okay? So like the integral of sigma omega is conserved, but again, the spectral weight also has to go at low frequency, just by locality. Oh, it does. It does as well. So omega depends on Q. So Q here is Q is not a wave vector or something. Q is the denominator of my rational thing. So here I'm assuming, so the only assumption I'm really making is that there's only one crossover scale. Okay, so I'm going to assume there's like a curve, and as you take Q to infinity, you just have a crossover and then it saturates, and otherwise it follows. So basically you follow the irrational curve for a while, and then you realize you're rational, so you saturate. Okay. Yeah. Yes, so that's what I'm going to do. I'm going to show how you can compute the exponent. Okay. So, all right, but the basic argument is, again, this shaded area here is the difference between the Judo weight. Okay, and so this actually gives you surprisingly highly non-trivial constraints. So you can kind of ignore this equation. This equation is just basically telling you precisely this, like this shaded area is the difference in Judo weight. And this difference in Judo weight, we know analytically it goes as 1 over Q squared. You just take the exact analytic formula. So as you approach with very large Q being denominator of the rational, your Judo weights, you approach the irrational Judo weight as 1 over Q squared. Okay. And so you can kind of plug basically plug those forms. So I'm assuming there's a power law divergence here. And I'm also assuming this diverges in some way with Q. Okay, so I'm assuming power law divergences and basically fixing the exponents once you do this. So this like relation actually gives you a highly non-trivial relation between those three things. So the way the AC conductivity is diverging at low frequency, okay, for the irrational point, that's this infinity. The way the DC conductivity, the regular part, is diverging as a function of Q. Q is the denominator of the rational approximant. And you see those exponents are related by just this seemingly trivial relation and this time scale, and it does depend on Q. And you see it's also fixed. Okay. So let me just pause on why this is kind of important, or why I think this relation is important. So it allows you to compute something that is actually way beyond generalized hydrodynamics, at least for now. Okay, so this is beyond diffusion, right? It's not ballistic, it's not diffusive, but it allows you to relate it to something that we actually know how to compute, and that's actually how I'm going to compute it, which is the DC value if you have a rational approximant. Okay? So I'm basically saying the way we can understand those like weird irrational points, okay, they're not that weird, they're actually dense, right? Like most points are actually irrational. We can take those rational approximants and understand how they behave. Okay? So we still need to compute alpha. So of course I haven't done really anything to compute what alpha is. Okay, but I'm claiming I can reduce the value to computing a DC conductivity. Yes. Yeah. So okay, so the regular part here. So this is, I'm assuming I have omega to the minus alpha. For this, okay, by assumption that just an ansatz I'm putting, it has to diverge if this diverges as this. So, okay, and then this one I can just Taylor expand around this. It's just regular. It has a DC value, and then you can put corrections. Okay, I didn't write them. I only put the DC value, but you can imagine you have corrections, and that's okay. This subleading, and then you just match everything powers on both sides. That's all, okay? And it gives you this. It's a few line calculation. So what we have achieved here is basically we can compute things that are anomalous from something that is not anomalous at all. Okay? And I'll show you can get this tail here, and actually you can also understand the KPZ point, the 1/3 exponent in this way. So I'll show you, and it's probably the simplest way I know to get this. Okay. All right, so now this is the only slide where I'm going to need GHD. The point is like this quantity by now is something we can compute. Okay? So that's a DC conductivity, it's finite, for a rational value. It's again only the regular part. And so this is using the formula by Jacopo, Denis Bernard, and Ben Doyon. So okay, you can kind of forget this. This is, you basically know from GHD all the scattering and all the quasi-particles that you have and how they scatter, what their velocities are, and you can analyze exactly what's going on in that soliton gas. The important point is, okay, you also have this formula from Jacopo and al. That you can compute this DC conductivity, and you can show analytically it scales as Q squared. So you can, of course, compute it numerically and see that it scales as Q squared. In that case, you can also show analytically it's not, okay, it's not very hard to show. So now you can just go back and say, okay, so this diverges as Q squared. It actually means alpha is 1/2, so that actually fix that other exponent. Okay? And that's it. So it tells you from, again, a DC calculation, which we know from GHD by now. So there's some knowledge here that you use GHD. But this implies something which is highly anomalous, which tells you that actually for, completely generically, if you take generic irrational value on that curve, you have a correction to this ballistic transport, which is completely anomalous. Okay? So I should say this is at any temperature. This is completely missed by Luttinger liquid. Okay? And I think that was also missed by any, I don't think this result appeared anywhere before. This is not something people have seen in numerics so far. I'll talk a bit about this. But it gives you this completely anomalous tail, omega to the minus 1/2. Okay, so it also gives you a time scale. So this time scale is a time scale it takes to realize you have a rational. So it's also, if you take a rational approximant, this is the time scale you need to measure the DC conductivity, say from DMRG. I would point out this is crazy large. Okay, so this is also why people are struggling to measure diffusion constants and check those formulas. Okay, so if you have a rational approximant with denominator Q, you need the time Q to the 4 to measure the diffusion constant. It's bad. Okay. So, okay. So just a few words for like the more GHD experts among you. So this time scale. So this is purely from computing the DC conductivity. It also makes sense from just thinking of the soliton gas and thinking of what happens microscopically. You can compute velocity, densities, and you can see that actually from this soliton gas, there's a simple mechanism that gives you this time scale, and it has to do with Levy's flights. Okay, so I won't go into this. So it's actually, if you want a conjecture that we have like the physical mechanism microscopically of why you have this is like the largest quasi-particles, which are the ones that carry spin, actually undergo some Levy flight. That is, they get very large rare kick, and you have a polar distribution, and get larger and larger kicks, and that's how you get this anomalous behavior. Okay? So this is a conjecture for now. It hasn't, again, been checked in numerics, but I think it follows naturally from this picture we have, that actually the spin, if you look at the spin-spin correlation function, it should have a Levy flight tail near the front. So I'm hoping this is something that could be checked numerically. All right, so this follows from like GHD. So let's say you don't like GHD. Let me give you a kind of like more physical picture of why you have this exponent. Okay, and it turns out it's actually very simple. It follows from Fermi golden rule. So, all right, so I should say before we did any calculation, we had an expectation, and that expectation turned out to be wrong. So it's always nice when that happens. Okay. So okay, we of course knew something had to happen at low frequency, and I think many people thought something would have to happen at low frequency. And the basic argument was the following, right? So we know if you take a rational approximant, we know from the approximation theorem the error is 1 over q squared. You have a denominator q. Okay, so it's a well-known fact, so that's your error. And the minimal thing is if you have two Hamiltonian and they differ again by epsilon, and epsilon is 1 over q squared, we should wait until time 1 over epsilon. See the difference. So that gives you q squared. Remember in my previous slide I have q to the 4. And so q squared would be alpha equals 0. Actually you can show you have a log correction. So this tells you you had to have a super diffusion in some way, but originally we thought it would only be a log, so something relatively like marginal. Okay. So when we did the calculation, we actually found something way more dramatic. Okay. So let me give you a simple argument, which is of course like after getting the result. Okay, we thought more about this, of why this could be true, and it has to do with Fermi golden rule. Okay. So why Fermi golden rule? So the key point is actually those, when you change this parameter, like when you approach an irrational point, so those points have completely different quasi-particle spectrum. So in particular, if you sit at an irrational point, you have infinitely many species of quasi-particles. They all have a dispersion relation. And when you take a rational approximant, you actually have a finite family of quasi-particles. So basically, when you go from this H infinity, which is the irrational point, and you add a tiny perturbation, you have infinitely many quasi-particles that have to decay. Okay? So this is like integrability breaking, right? So when you think of integrability breaking, no one would argue with me. I think if I tell you, you take an integrable system, you add a perturbation, we think the rate should go with perturbation square. Okay? Here, of course, it's not integrability breaking. I have integrability on every time. But whenever I turn on this perturbation, I have infinitely many quasi-particles that have to decay in a continuum. Okay? So now if I say my just rate is like epsilon squared, I get this q to the 4. Again, okay, how much you trust this is, again, it's after the calculation. I don't know how to make this very precise, but it's not completely crazy that we get this. Okay, so this is the part that went wrong. Okay, and so if you assume this process is incoherent and you have quasi-particles that will have to decay somewhere and put Fermi golden rule, this gives you naturally this time scale. This time scale gives you this. Okay. All right, so in the last like 6 minutes I have, let me tell you a few things about numerics and about KPZ. So numerical evidence, okay, so at the time when we wrote our paper, we tried to do numerics on the XXZ chain. It turns out it's very hard to see this tail, okay? You can kind of see maybe something polar, but it's very hard to measure. So actually the data I'm showing is data that Marco shared with me, which is also in that paper. So they have a discrete, I'm not gonna go into the details, this is a slightly different model. It's actually a discrete time Heisenberg model, okay? But it has this same feature where you have a Drude weights. So here it's kind of flattened for the figure, and it has this fractal structure. Okay? And so the different lines that you see are like DMRG data for this, that they see for this model at different times. So I think it's a very beautiful plot. So of course, as you see from this, like the data they see is not fractal, right? They see something continuous, of course. But you see they kind of nicely see all those peaks in their numerics, okay, as you approach it. So two things here. So something they already had in their paper, but I didn't realize it was actually related, is they see that the width of those peaks it closes as 1 over square root time. It's actually 1 over square root time is actually this. So you see epsilon is like the difference in your Hamiltonian. So here it's like the anisotropy. Okay, so this tells you have a time scale. So if you have a given epsilon, it should swell as 1 over square root of the time. So this is actually what they see here. Okay, this is kind of an indirect prediction. The more direct prediction would be like if you take a good irrational somewhere where you don't have a peak and you look at how this decays, it should be 1 over square root of time. So you can try to look at this, and again, this is just data that Marco shared with me, which is not, okay, I'm not guaranteeing this is fully converged or anything and so on, but this is just to show that, okay, this looks pretty well power law, and they can go to very long times here. And okay, if you fit it, actually, you get exponents very close to 1/2. Okay, so again, with caveats and so on. But I'm kind of hopeful that at least maybe not in XXZ directly, but in those modified setups, you can actually check this and see this anomalous transport. Okay. So finally, let me go back to KPZ and to this isotropic point you heard a lot about. And so I claim you can understand it perfectly from this argument coming from the isotropic point. Okay, so how does it work? Well, let me take a series again of rational that will approach this isotropic point. So let me take delta of q is cosine pi over q. So you say when q goes to infinity, of course, this gives you delta equals 1. That's the isotropic point. But at this point, you see it's slightly different because the Drude weight is vanishing. Okay, so I'm like approaching this with a series of rational. Okay. But actually, the same story holds. Okay, so the Drude weight is like decreasing, and it has to go somewhere. And at the same time, and the exact same argument of conservation of spectral weight has to apply. The only difference is here you can compute the DC conductivity associated with this, and this is something Jacopo did even at the time, like last year, right? And so it actually scales with Q. So it's something that's also pretty easy to show. And if you just go back to my formulas, and so now you have an exponent 1 instead of 2, you plug it in there, it just gives you exactly this right away, that you have to have omega 2 minus 1/3. So as far as I know, this is probably actually, at least to my taste, it's the cleanest derivation, at least of that exponent. Okay? So there's almost no assumption. I mean, if you believe this result, basically, and you're okay with my with the fact that I only assume 1 time scale, which I think is perfectly reasonable, you get this immediately. So basically, I'm saying that this KPZ or whatever, well, okay, I'm not showing KPZ here, just to be clear, I'm only showing this exponent, 1/3. Okay, but at least this exponent 1/3 follows directly from what we know in the gapless phase. Okay? So this is nice because previously we had arguments coming from the gapped phase, now we have arguments coming from the gapless phase, and they give the same type of results. Okay? So the spectral weight argument basically gives you all those anomalous exponents almost for free. Not entirely true. I mean, I'm relying on the fact that we know at least the DC values. All right, and so with this, I'm just going to wrap up. So this is, okay, the main conclusion is that, as I said, it's like a mystery of the fractal Drude weight in the sense that it's a mystery in the sense that many people were unhappy with this. I think it makes perfect sense, and it's, if you assume something weird is going on at low frequency, and I think it's, in retrospect, it's kind of obvious that something like this had to happen. So the nice thing is it gives you a new anomalous tail, which was not predicted before, and that I hope we can see in numerics. So I wrote a slightly provocative statement here, which of course is not entirely true, that transport in integrable systems is actually generically anomalous. Okay? So of course, again, it's not entirely true. What I mean by this is that, so I don't think you only have like this isotropic point where you get KPZ and everything else is like nice and diffusive or ballistic. You see that whenever you have infinitely many quasi-particles, so here it's like strings in XXZ, okay, so you will have probably this anomalous transport. And Sarang talked about other regimes where you see similar things. And so I think it's actually pretty generic in systems where you will have those bound states, this hierarchy of bound state excitations. Okay, so this should be true in classical and quantum systems. You probably have all this anomalous stuff. And of course, one question that would be kind of nice to wrap our head around is if you can classify all types of universality classes of spin dynamics, and we know we can have diffusion. Probably we have KPZ at this point. Here I'm arguing that I think you have Levy flight type corrections in some regimes, and there could be others, of course. So with this, let me thank you for attention. Thank you.
Some questions? Yes. What is the dynamical exponent for the super diffusion in, they say 1 over omega to the 1/2 on to
yes. Okay, I always have to actually compute it, but yes. I mean, like, it means like the variance goes as t to the fourth third. Anyway, I can compute it, yes. I mean, it's not
larger than 2/3, or do you think?
okay. I mean, we can do this on the board, right? But okay, I just need to go compute it every time. But yes, I mean, it is super diffusive. I want to say it, yeah.
Okay, but
Okay,
anyway,
yes.
but you say that it's a Levy process.
It is, yes. I think, well, okay, so the Levy thing is not something we get for sure as the rest. The Levy picture came from like thinking of a soliton gas. So if you think of this interpretation in the soliton gas, the reason you have this is you have like just the largest quasi-particle, which is charged, is like having larger and larger kicks. That's what gives you this anomalous process. That's the Levy mechanism. But yeah, so this gives you like a clear prediction for what the spin front should be. So it should have parallel tails. So it's not only, just like you have the KPZ function, here it should be a Levy function. So I can give you the dynamical exponent right after. I just need to like recompute it.
Any other question?
Also in HYDRODY, I don't know how to have models like this, right? So there's no, yeah. So all those models, like of course, like Bethe-Ansatz integrability works only in 1D. So there's nothing, and of course I should say like everything I told you relies a lot on integrability, right? So I don't expect all of this, any of this to survive once you break integrability. Of course it's gonna survive for long times and well, maybe not so long, like depending on what you call long, okay? But all of this, of course, the reason you have this tail is because you have a hierarchy of quasi-particles. So the minute they decay, this is gonna go away. What do you mean? So I don't know any integrable model in the way I'm talking. So that's what I mean, like all the models I'm talking about here, like they rely on Bethe-Ansatz solution and it works only in 1D.
Thanks a lot. Yes.
Thanks.